Hello everyone and welcome to another episode of OrgoSolver. Today we're going to be going over the IUPAC naming conventions for alkenes. So let's get started. So going over briefly our lesson from last time of naming alkanes, we know that what we're trying to do is count the carbon chain here. So what we can see is that we've got carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and that would make it pentane. Now, if we added, say, a molecule here, that would then change the whole skeleton. Even though we would have 6 carbons, we would then start counting from here. Again, 1, 2, 3, 4, 5, with another carbon here. And this would be our methyl group. So expanding that, let's move into what it would look like with a double bond or an alkene. So very quickly, we're just going to go over some of the names of the most basic alkenes. So basically, you start out with, because it requires a double bond, you can't have anything smaller than 2 carbons. So here we can see we've got carbon 1 and carbon 2. So here, the molecule name with those 2 carbons is going to be ethene. And that's correct that we see that there. As we keep adding carbons, we keep following the naming conventions for the basic carbon chain and the basic carbon skeleton. So originally when we had alkanes, it was methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. Here we're going to have the same kind of naming convention, except you're going to notice that's just replaced with an E and E. So here we had ethene earlier. This one has 3 carbons, so this would be propene, and we'll get into why it's prop-1ene, but-1ene, pent-1ene, and so on and so forth. So we're just changing the alkane name, alkanes are single bonds, A and E, to ene, E-N-E, for double bonds. So let's try our first example here. So we've got a 6 carbon molecule, okay? So again, 1, 2, 3, 4, 5, and 6 is over here on the right. All right, so now that we can see that better, we get these 6 carbon atoms. So this would just be hexane, right? Now, as soon as we add a double bond, that changes the name. So if we add it here on this position, we're going to see that the name of the whole molecule is hex-1-ene. So what happened here is that it's still hex. Hex means 6. The ene gets added because now they're signifying that there's something different with this molecule that's got a double bond. And the 1 is telling you where that double bond is. So looking at our naming convention, here is 1, carbon 1 and carbon 2, and we're counting from where the double bond starts. So in this case, it wouldn't be hex-2-ene, it would be hex-1-ene. So now, let's try and expand on this. What would happen if we added the double bond here? So now we have 2 double bonds. We have a double bond here on carbon 1 to 2, so it's carbon 1 is the focus here. Now a carbon-carbon double bond between carbons 5 and 6. Using our naming convention where we're taking the first carbon that it's attached to, we would see that this is hexene, right? So 6 carbons, but there's going to be 2 double bonds. So that's going to make it a hexadiene. And the way we're going to name it is based on where the carbon atoms have double bonds. So in this case, carbon 1 has a double bond, carbon 5 has a double bond. So 2 double bonds, and as we learned in our previous lesson, when you've got two functional groups, it'll have a prefix of di, 3 functional groups tri. So in this case, we would expect this molecule to be 1 and 5, but the naming convention is that the alkane skeleton goes in front, and then you start naming where the double bonds are. So what we would see here is that it's going to start with a hex because there's 6, 1, 5, diene. So it's going to be hexa-1,5-diene. And sure enough, that's what we see. So it is a little bit more involved than just naming alkanes, but we're going to work through it and check out some different examples. So building on what we've done before, let's add a functional group here. So all we did is we just added a methyl group here to carbon 2. Now, our carbon skeleton is still functionally the same, right? So we have this other molecule, or this other functional group here, which could be the start of your naming convention, right? 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. So how do we know which one to use? Well, the best way to do it is to recognize that we're going with the double bond as though it's part of the carbon skeleton, and that this is a functional group as a separate methyl group. So what we'd expect to see here is that because this methyl group here is attached to carbon 2, this would be 2-methyl hexa-1,5-diene. So let's test what our hypothesis would be there. 2-methyl hexa-1,5-diene. Again, this methyl group is on carbon 2, and that's where the 2-methyl comes from. And the hexa is the 6-carbon backbone here. 1,5 representing where the 2 double bonds are, and diene telling you that there are 2 double bonds. So now let's try a different example. What happens when we have an alkene that has the functional group as a double bond? So here we've got, let me zoom out. This should be, let's practice our alkane naming here just for completeness. So how many carbons do we have? So we have carbon 1, 2, 3, 4, 5, 6, and 7. That makes it a heptane. All right. So now, to this heptane molecule, let's add a double bond right here. So we've added a double bond to carbon 4, attached to another carbon here as a functional group. This doesn't change the skeleton, as this carbon is by itself right here at the top, and it wouldn't make a skeleton. If you were counting this carbon, it would be 1, 2, let me just number it with these blue numbers. You could have 1, 2, 3, 4, 5. So that in that instance, our carbon backbone becomes short, which is against the rules of IUPAC naming. So we're going to count this as a functional group and still go on with this 7-carbon backbone. So when you add a double bond here as a functional group, that'll be a methylidine group. If you remember, a single bond is called a methyl group. So a double bond added as a functional group is a methylidine group. And so again, if we look at where this methylidine group occurs, it occurs on carbon number 4. So we would expect the name here to be 4-methylidine heptane. Heptane, again, it's in heptane, not heptene, because the double bond is not part of the carbon backbone. Methylidine is the name given of the functional group that has a double bonded carbon to it. So let's go ahead and check our work. 4-methylidine heptane. All right, pretty good. Now we're cruising through here. So now what happens if we change the functional group a little bit? So if you remember, as a functional group that we were working on in the alkanes, if I added 2 carbons, this would be an ethyl group, right? Because we've got methane, ethane, butane, right? Or propane, then butane. So if you were to add those groups, you would be adding a methyl group, an ethyl group, a propyl group, or a butyl group. In this case, this was a methylidine group, so it stands to reason that it should be called something similar, and sure enough it is, it's called an ethylidine group. So this molecule, with this extra added methyl group to the methylidine group, turns it into an ethylidine group. If you can follow the naming convention there, going meth, eth for 1, 2 is the number of carbons. So here again we see that we have the 7 carbons, and on the 4th group here, on the 4th carbon, it's an ethyl group because there's actually 1 and 2 other carbons here, making it ethyl, but because it's got a double bond, it's an ethylidine group. Now, let's get into a subject that we didn't really touch on in the last video, so it's important to start going over it at some point. So if we go to our ring structure tool, we can draw just a simple ring here. Now, using our alkane naming convention, we're going to count the carbons here. This is carbon 1, 2, 3, 4, 5, and 6. And if you'll notice, because the molecule is completely symmetrical, there are no functional groups, it doesn't matter where you start numbering specifically for this example because they are all the same. So here we have, 6 carbons, which makes it a hexane, but because they're in a joined ring, this molecule is called cyclohexane. So let's try this with another molecule. So before we begin, if you can guess what this is, that's great. If you need a little assistance, let me help out. This is cyclopentane because there are 5 carbons, and 5 from our carbon naming skeleton is pent or penta. Now, what happens when we add a double bond? We change the naming convention. Remember, alkanes, single bonds, end in ane, right here, ane. So this should theoretically end in ene. So let's see. Is this called cyclopentene? It is. Because there are no other functional groups, it's okay to say cyclopentene because there's only one, so you don't have to worry about 2 different positions. Otherwise, theoretically, we can go through an example and see what it would look like. Let's just clear the board here. So, what happens if we add another double bond here? Going back to our first example, we remember that, okay, so we've got 5 carbons, but now we might need to start wondering how we name them. So what we want to do is we want to name them in an order where we capture all of the functional or different groups before we get to the alkenes. So what I mean by that is, starting from this carbon, we're going to count 1, 2, 3, 4, 5. What we do not want to count is in the opposite direction. We do not want to do 1, 2, 3, 4, 5, because this creates a gap between the 2 double bonds of almost 1 extra carbon. And what we would expect to see is that on our carbon numbering, we have carbon number, remember, 1, 2, 3, 4, 5. We have cyclopentadiene, again, cyclopenta 1,3-diene because the double bond starts here on carbon 1. It does touch number 2, but it's still part of this first carbon. The next carbon that has a double bond is here on number 3, which is where we get 1 and 3. Let's try one more example to help solidify this. we've got our pentene molecule. Now, what happens when we add a double bond as a functional group? When we added single bonds, these are methyl groups. A single bond, this would be a methyl group added. You add another carbon to this, and this is an ethyl group added because there are 2 additional carbons, and if we remember from our naming, 1 is methyl, 2 is ethyl, and 3 is propyl. Now, we have a double bond. And if you remember from the earlier example, we add the lidine suffix to these compared to their alkane counterparts. So this, because it has 1 carbon on the double bond, this carbon is part of the pentane ring. Remember the pentane ring, because there are no double bonds inside the ring, the double bond is existing out here, and there is 1 carbon, so this is a methylidine group. So we would expect that this molecule's name would be methylidine cyclopentane. I think it would also be correct to say that it's 1 methylidine cyclopentane. However, because there are no other functional groups, you don't need to specify where it is. So building on that, we would expect that this is 1 carbon. If we had 2 carbons, we would have an ethylidine group. So let's try that out. Let's add 1 more carbon here to the double bond. So we've got an ethylidine functional group. And here we go, we've got ethylidine cyclopentane. All right, let's do 1 final example to bring it all home. So we're going to start out with this molecule that we now know is called hexane, cyclohexane. Let's add 2 double bonds, like that, and why don't we throw on a double bond right there. So, if you ignore my earlier error of calling it just hexane, and we are working off of this molecule called cyclohexane, it's good practice to start numbering. So, we're going to have a little bit of a dilemma here. Where is the best place to start numbering? Do we want to number starting here, where the methylidine group has been added? Do we want to add it here and count in this direction? Or do we want to start here and count all the way in this direction? Let's try 2 different ways and see which one sounds and works out better. In the first example, let's start counting from this carbon here. So we have carbon 1, 2, 3, 4, 5, 6. So in this example, we would expect it to be 6 methylidine cyclohexa, and our double bonds are on 1 and 3. 1, 3, diene. So that would be if we counted in this direction. But there's another direction we might be able to count in. What if we wanted to start with this carbon as our carbon number 1? So we're going to draw it in blue here. 1, 2, 3, 4, 5, 6. Now in this example, our methylidine group is addressed earlier, and we still go in one direction and capture both of the double bond or alkene groups here. So in this example, because we've got the functional group gets named first, it's going to be 5 with the blue. Again, methylidine. Still cyclohexa because the carbon skeleton hasn't changed. And interestingly enough, we still have the double bonds occurring on the 1 and 3 carbon, and we still have 2 of them, so it's still a diene. So let's check our work. All right. Let's undo that. So we've got 2 predictions here. Which one is it going to be? As we can see, blue wins. The reason for this is because of the positioning of the molecules. So a good trick whenever you're naming the molecules is you might be tempted to start just counting anywhere. And that's good to start figuring out what your carbon skeleton looks like and what your base skeleton name is going to be. But then it's important to evaluate how the functional groups and double bonds and other molecules, which we'll get into in other lessons, are organized in the order of the direction that you're counting. So as you can see in both examples, we started counting within the cyclohexane ring as carbon 1. We didn't pick the functional group to be carbon 1. So you might be thinking, would it have been correct to start here and just go 1, 2, 3, 4, 5, 6. And I apologize for all the colors mashing up there. But in this case, what would we have had? 1 methylidine, still cyclohexa because the carbon skeleton is still in a cyclo configuration. But now it would have been 2, 4 diene. And the naming convention for this requires that the carbon skeleton has the lowest priority, and then the added functional groups will then have whatever priority is assigned to them as you're naming through the molecule. I hope this lesson was helpful. I know that this can be a lot of information, but I strongly encourage you to get onto our website, orgosolver.com, go to the molecule namer suite, and go ahead and just try and draw and name as many molecules as you can. It's important to just see and visually address what affects the name of a molecule and how this can shape your understanding of how we name molecules, so that when you're learning and very quickly, and your professors may be saying, oh, we're just going to add a methyl group here, and suddenly we've got some sort of hexane, you can keep up with them because you know, okay, hex means 6, hexane, that means the carbon backbone is 6, and methyl or methylidine, okay, I know what those functional groups are. So thank you all for your time. Make sure that you check out our website and hit like and subscribe for our video, and I will see you chemists next time.